So, good afternoon in Europe or good morning in Western United States. I would like to welcome you to our third webinar series on technical issues concerning the use of geothermal energy in district heating and cooling grids. Today we will focus on petrothermal energy, or also call it unconventional geothermal energy. Before we start with our workshop, please some of our communication rules. So you're automatically muted when you're entering our room. So this room is not like a typical webinar software. It's very open, and this is also what we would like to support, to have an open discussion and not be so restrictive. But just to ensure that everybody has a good connection, please turn off your videos and your microphones and use the chat window of WebEx to post your comments and questions. My colleague Vasiliki, who will be the moderator of the chat, will forward your questions to the speakers after each presentation. And in the end of our workshop today, there will be also a possibility to open the mic and we can have a discussion. So I see that already 30 participants joined this workshop. So we have more than 80 registrations, which is very nice. And we will start now with our workshop. So my name is Gregor Götzl. I'm working at the Geological Survey of Austria in geothermal energy, and I'm chair of the cost action Geothermal-DHC, which is hosting this workshop today. Our previous two workshops inside Geothermal-DHC were addressing very specific context, the use of geothermal energy on volcanic islands. This was in October last year. And in January this year, we had a workshop on shallow geothermal energy. And this is the third one in this series. About the program today, I would like to say a few words in the beginning, but not too long, about, of course, the action and the motivation to organize this workshop from my point of view. Then I'm very happy that we have two excellent keynote speakers. First is Joseph Moore from the University of Utah, talking about the Utah Forge EGS laboratory, and followed by Albert Chanter from ES Geothermie in France, where we will look at an already existing EGS installations at two sites in France, in Sulz-sur-Forêt and Rittershoven. We will switch then a little bit the order, and I would like to invite then my colleague Antonin Tim from the University of Prague to speak about an ongoing EGS project or in a preparational phase in the Czech Republic. And finally, we switch a little bit the topic and we go from utilization and field laboratories to exploration. And my colleague Emilio Moyer from the Spanish Geological Survey will speak about geothermal exploration outside of the typical known hydrocarbon regions, where we have a lot of data based on wells and seismic exploration, which can also be useful for petrothermal energy use, especially in hard rock environment. Our workshop is planned until 7:30, so maybe hopefully we can end a little bit earlier, depends on the discussion in the end. And I'm very happy to have you all here. And I would like to start with one important note. Please note that this workshop is recorded and is streamed at our YouTube channel. So it will be available at our website, the recording of this workshop, and you get the documentation of this workshop afterwards. I have all your email contacts, and even if you have any further questions to the speakers, you can write me after the workshop and I will establish the contact. So I will now speak a little briefly about cost action Geothermal-DHC, and yes, my question or my idea in this context, petrothermal energy for use, not just for electricity, but also for retrofitted conventional district heating systems. And I put there a question mark because probably this is a quite new topic. So what is Geothermal-DHC about? It's not a research project, it's a scientific network funded by the European Union within the cost framework, the cost program. So that means that it's an open, accessible research network. Currently, we have 150 researchers from over 39 countries in Europe, but also outside of Europe. And we're looking at the integration of geothermal energy in decarbonized heating and cooling networks. So our focus is on the heating and cooling sector, not so much on electricity, but of course, combined heat and power can also be an option inside this framework. Yes, I'm the chair of this cost action together with my colleague Dejan Milenic from the University of Belgrade. If you would like to inform yourself or would like to join this network, it's open accessible. Just visit our website. So we're looking at so-called new typologies of district heating networks, and this applies to all ranges from the newest generation, 5th generation low temperature grids to older conventional retrofitted grids. So we're looking at a twofold role of geothermal. Classically, of course, with a heat supply that would be especially for baseload, but which is more and more emerging as a topic, also using geothermal as a storage. So a new typology and or topologies of such heating grids, they are not so much hierarchically centralized anymore, but they are, let's say, organized in grids, in circular grids, where even the roles of consumers may change to prosumers producing waste heat and having heat pumps as kind of a moderator of these new typologies. In Geothermal-DHC, we look at the full technological range of geothermal energy, not just on direct heat use, but also on shallow geothermal, and try to match it with the different generations of district heating and cooling grids. Primarily, we're looking at heat production and heat storage, but not entirely. We also look at cooling from free cooling to high temperature cooling using absorption heat pumps. And we would like to demonstrate that geothermal can be a major technology in future heating and cooling networks. Today we talk about unconventional, we called it unconventional geothermal. So what does conventional mean? So I also use the term hydrogeothermal. So you have an aquifer system having enough hydraulic productivity, enough yield to produce natural thermal water, which you then use in a heat exchanger for supply of heat. So unconventional or petrothermal, geothermal energy goes into the field where you don't have enough natural reservoir. So you need to stimulate or engineer the system to establish heat exchanger surfaces in the subsurface. And this is of course, it's not a strict border between conventional and unconventional. So you can always also use these stimulation techniques to enhance the productivity of an existing low permeable reservoir, which is also known as the EGS concept, where you have a lot of natural fractures, or you directly go into low fractured crystalline block when you go and really produce all the heat exchanger surfaces by yourself, which to my understanding is more or less this early HDR, hot dry rock concept. Both systems have advantages and disadvantages, of course, and we might discuss them later on in this workshop. So I looked at the publication from the year 2017. It's not the most recent one. I wanted to know how many of these EGS sites exist. And based on this publication, we can estimate around 18 sites. I think, I'm not sure if this number is still correct, also including abandoned projects. What we can observe is that the technology of enhanced geothermal systems already started in the 1970s in the United States. And I would say until then, it didn't really leave the pilot and demonstration phase. In this paper, the author proposes a technical potential for EGS on electricity production worldwide for around 1,200 gigawatts at a probability of 70% and the so-called 2050 reserve. So the share which is also economically feasible in production around 70 gigawatt. You can multiply this number by 5 to 10, which if you apply combined heat and power and would have the same amount then for heating. But what I also observe, and I'm working in geothermal since the mid of the 2000s, that after, let's say, a very enthusiastic time in around 2010, 2011, I recognize that there is somehow reduced research and development activities in petrothermal energy in Europe. And of course, it might be linked to technical issues, but I put a question mark there because maybe there are also reasons why research and development was not really increasing in the last 10 years, and maybe we'll have to look at new opportunities to use petrothermal energy. And that's why we organized this webinar today. So one idea which we like to follow in Geothermal-DHC is to use this technology for retrofitted district heating systems, which currently still run on coal, oil, or gas, but need to be retrofitted in the next 10 years in order to fulfill the policies and requirements of the European Union or Europe in general. And there are lots of these district heating systems still existing, and many of them, they are not inside the typical hydrogeothermal resource zones, as you see here on this map. This is from the GeoDH project, the map on the right-hand side. And they say, where you don't have hydrogeothermal, you have shallow geothermal. But I would like to expand this and say, yes, you would also have petrothermal energy where you don't have the classical hydrogeothermal resources. And that brought us to these three main questions, which I would like to ask all of you again at the end of these workshops in our discussion rounds. How you evaluate the chance and the opportunities that petrothermal can be an option for all dependent district heat systems, which need to be retrofitted and will be probably retrofitted in the next 10 to 20 years. And what does it needs to make petrothermal also attractive in such areas where you don't have the classical high geothermal gradient, high temperature zones, and what kind of research needs to be executed to make petrothermal really market ready. And with this, I would like to close my introduction. I don't want to speak too much, and I would like to give the floor to Joseph Moore from the University of Utah to talk about the Utah Frontier Observatory for Research in Geothermal Energy, so Utah Forge. And I'm very curious for your presentation. So floor is yours, Joe.
Thank you very much. I appreciate the introduction, and I appreciate your introduction. Welcome, and for most of you, good afternoon. My name is Joe Moore, and I'm the project manager of the FORGE project, Frontier Observatory for Research in Geothermal Energy. And I'm going to close my video, and you can watch the slides. We did it?
I don't know how to close the video.
All right. If not, we'll just go ahead. Picture of the drill rig that we've been using. As Gregor mentioned, Enhanced Geothermal Systems offer the opportunity to utilize geothermal energy anywhere in the world. But unlike conventional systems, EGS requires permeability enhancement. This can be done chemically in limestones, for example, by injection of cold water. This was done at Desert Peak and Ref River, or by hydraulic stimulation, which is the technique that we will use at the Forge site. Despite more than a dozen attempts over the last 40 years or so to engineer permeability needed to create geothermal reservoirs, this has been challenging. In fact, it's been much more challenging than we expected. The first projects were conducted in New Mexico, the Hot Dry Rock project. But since then, there have been a number of projects in Australia, England, France, Japan, South Korea, most recently, Switzerland, of course, and the US. Well, some progress has been made, and I don't want to denigrate the progress. The overall results have been really disappointing. No commercial size EGS geothermal systems have been developed. Let's talk 10 megawatts or more. And tracer data show that only a small volume of the seismic clouds produced by hydraulic stimulation had interconnected permeability. And we're talking here of just a few percent. Because high pressures are required to break down the reservoir rocks, there is now a general consensus that reservoir formation is best accomplished by opening existing fractures that are optimally oriented in the current stress field through hydroshearing. And an example of this is shown on the right, a sealed fracture, which then shears under relatively low pressure, creating wormholes, and these wormholes then provide the pathways for the water to move through the reservoir. In 2014, the U.S. Department of Energy issued a request for proposals to build and operate an underground laboratory where tools and technologies for EGS development could be tested. This is an important point because the proposal did not require electric generation, unlike most of the other projects which were aimed toward generating electricity. The DOE concluded that ideal conditions were temperatures greater than 175 at depths greater than 1.5 kilometers, low permeability rock, principally granite, low risk of induced seismicity. I won't talk much about it, but it's been a problem in many sites. Low risk of environmental impacts to the existing animals and plants, and no evidence of a convective hydrothermal system. So truly a brownfield environment. 5 sites were proposed by 4 teams. 2 of the sites, one in Utah and one in Nevada, were selected for further consideration. And in 2016, each of the 2 teams drilled a 10,000 foot, 3 kilometer well to prove that the conditions were met. The team, DOE team, eventually concluded that conditions were best met in Utah. And so the project was given to us. Okay. Most of the previous EGS experiments have attempted to stimulate long sections of open hole. This has some obvious problems, particularly that the fluid will leave at the first entry, and it's very difficult to stimulate lower entries. The alternative approach, and the one we are taking, is to stimulate fractures behind casing. This is the more standard oil and gas approach of stimulating distinct stages along a well. This will require advances in stimulation and well completion techniques, high temperature tools, and zonal isolation technologies. Utilizing existing fractures for reservoir creation will require managing and modifying the existing native stress field while minimizing induced seismicity. In addition to the work that we are doing, and we are primarily on the operational side of the project, external research is being conducted by national laboratories, private companies, and universities. This year, 19 R&D projects will receive funding for a total of $46 million. The Forge project is located in south central Utah. The map on the right shows you where Utah is. About 350 kilometers from Salt Lake City. And if you happen to travel in equal distance to the south, you'll eventually get to Las Vegas, where you can spend your money differently and not on wells. The site is located at the transition between the Basin Range and the Colorado Plateau, which is an area of normal faulting and extension. This has given rise to several geothermal systems in this area. The map shows our key partners. There are many of them, several dozen. They include private companies, laboratories, government agencies, of course, and private consultants. In addition, we are working closely with researchers from GeoEnergy Swiss, Jilin University in China, and Sequent in New Zealand. If you wish to collaborate with us, please let me know. Get in touch with us, and we can talk about that. We're always looking for collaborators. Okay, the Forge site is situated in Utah's renewable energy corridor, 16 kilometers from the nearest town, which is Milford. Milford is a rural community, mostly farming, with a population of 1,400 people. The site is nestled between a solar field. You see the blue area on the far left of the slide. Okay. Wind farm, there are 168 windmills, and the Blundell Geothermal plant, which produces 36 megawatts. Good? Okay. To the south is another geothermal field, Cirque's geothermal field, produces 12 megawatts, and a biogas facility. Okay. Significantly, there are no endangered species in the area. There's no nearby human activity, and there's no potable water. There is groundwater, but all of the groundwater is naturally contaminated or contains hazardous chemicals. It contains arsenic, antimony, boron, chlorine, fluorine. And so it can't be used for agriculture or for drinking. And as a result, the project doesn't compete with any other human activities. And that's important in this area. Okay. The geology of the area is dominated by tertiary granite that forms the core of the mineral mountains. And this is shown in a lime green color. The red and the purple rocks on the geologic map are rhyolites that were in place around 750,000 years ago. A still cooling magma body underlies the range and provides heat to the area. The Blundell plant lies east of the Opal Mound Fault and the Negro Mag or Mag Lee Fault. And you can see a number of wells labeled. 54-3 is one of the production wells. Okay? Black dots are gradient wells drilled throughout the area. Okay, these production wells originally produced fluids at about 250 degrees C. So it's quite a hot geothermal system. In fact, it's one of the hottest in the Western US. Since the late 1970s, there's been extensive geologic, geophysical, and geochemical studies in support of geothermal development. And we have completed new seismic reflection and geochemical studies, which have helped expand our understanding of the region. The core samples are our typical core that came from wells drilled in the Forge site. Top two from well 5832 and the bottom from 16A. The top two are some of the granites. There are about 5 different granitic rocks ranging from quartz, monzonite to true granites that you can see in the top. And then the lower one is a metamorphic rock that was intersected at the bottom of 16A. And this rock is exposed at the very western edge of the mineral mountains, and you can see it in a gray color. That was the only intersection of the metamorphic rocks in the cores that we collected, or in the rocks we drilled through. Okay. Beneath the Forge site, the contact between the basin deposits and the underlying granitic rocks dips westward at approximately 25 degrees. The upper figure is a seismic reflection profile across the site. The lower one is the geologic interpretation. This is a major fault zone. Most of the basins and ranges in the Western US in the Basin and Range Project are separated by very steeply dipping faults. There's good evidence that the contact is a fault contact. It's highly sheared. The granite is sheared. But this particular fault is interpreted as a rotated fault that was rotated down to the down to the east, I'm sorry, to its present 25-degree dip. The fault appears to be locked. There's no evidence of any movement along it. The sediments lap up unconformably against it. Based on the seismic data, we have found no offsets of the contact between the fault and the overlying deposits. And this is important, right? One of the goals is to minimize induced seismicity. And we can help ensure that we do minimize seismicity by demonstrating there are no active faults in the region. And at this site, no active faults have been identified. The faults that you saw trending north-south, you'll see them again in the next slide, do not extend into the basement. These are very shallow faults in the alluvial deposits. Okay. Here's a digital terrain map. Again, you can see the deep wells in green, and the black wells are shallow gradient wells. We can see that north-south trending group of shallow faults that does not extend into the Ford site, and two other structures, the Opal Mound Fault and the Mag Lee Fault. The Opal Mound Fault appears to be a relatively insignificant structure. There's about 15 meters of displacement on the east side, and it appears to control the vent for the silica deposits for the sinter that formed about where the D in Opal Mound is. The vent is now sealed. There's no evidence of shearing, and you could see that in the figure, the photograph in the lower right. Despite this fault apparently being insignificant, it has a major control on the hydrology and thermal structure of the area. Wells east of the fault within the Roosevelt Hot Spring geothermal system, where the Blundell power plant is, are characterized by higher pressures than wells to the west by the Ford zone. We're not sure what the explanation is, but there are enough wells to demonstrate that this is the case. The Opal Mound Fault also acts as a thermal barrier, and this is due primarily to permeability differences. To the east of the Opal Mound, temperatures are convective. You can see on the far right, it says Roosevelt Hot Springs Hydrothermal Reservoir. 10 wells, they basically have constant temperatures with depth, very convective regime. To the west, demonstrated by 58, but also by a Ford, a 12,000-foot well, and other wells that we have drilled, the regimes are conductive. That is, temperatures increase with depth. There is no evidence of a hydrothermal system, as would be indicated, say by convection. Okay? The box on this slide shows the DO8 criteria for a Ford reservoir. Okay. Well, the project has been ongoing for a few years now. This is a drone shot of the current infrastructure. 5 wells have been drilled. The wells 16A 7832 was completed in January. I'll talk more about that. This will be the injection well of the production injection well pad. The remaining wells 58, 68, 56, and 78 will be used for seismic monitoring. 6832 has a seismometer and accelerometer in it. It's about 1,000 feet, 300 meters. Okay? And 78 32 has a DAS cable, a fiber optic cable, down to about 3,000 feet. Sorry, I'm changing units to you. 5832 is the first well that was drilled. The inset shows the forge site with the wells in it, and two rings that will contain borehole seismometers. The first ring will be 3 kilometers from forge center, and the second ring will be 8 kilometers from the center. The boreholes will be about 50 meters deep, and they're basically designed to identify any runaway fractures that may form during the stimulation or later. Microseismicity has been monitored since 1981 by University of Utah seismic stations. The events occur in 3 clusters. The quarry events are caused by blasting. They're not natural. Natural events occur at the airport and Milford. We've seen magnitudes of 4 in the past. And then there are those that occur in the mineral mountains. Notice that there are no events in the forge site, at least above 1.5 magnitude. In 2016, high-resolution broadband instruments were put in that can monitor below 0, and we have not seen any events there. Within the mineral range, the green are mostly shallow, and these are related to injection at the Blundell power plant. And then the other colors, red and blue and green, are related to an east-west structure approximately parallel to the Mag-Lee fault. And these were active back in early 1980s, late 70s, and then again sporadically over the last few years. Overall, what we see are low rates of seismic activity and low magnitudes, typically less than 1.5. Drilling the granite has been quite challenging, much more challenging than we had expected. The 2 most recently drilled wells, that was 16A 78, 32, and 56, were drilled with PDC bits that had been specifically modified. These are polycrystalline diamond composite bits. They're quite common in the oil and gas industry, but they had virtually never been used in the geothermal industry, using tricone bits instead. These bits proved to be far superior than the tricone bits. 16A was drilled and cased to nearly 3,350 meters with 7-inch casing. The well was drilled vertically to 1,800 meters, deviated 65 degrees, and then drilled the total length of, as I said, 334 meters. It reached a true vertical depth of 2603 meters. We don't know what the temperature is yet. We haven't been able to get a temperature tool down around the curve, but it's guessed to be somewhere around 240 C. To my knowledge, this is the first time a highly deviated, large diameter well has been drilled strictly for geothermal applications in hot abrasive granite. If you know of others, let me know. The 65 degree was specifically selected because it was thought that we might just be able to get wireline tools around the curve. Turned out to be wrong. There's some other observations and suggestions have. Anyway, continuing, the well drilling was optimized using physics-based mechanical specific energy (MSE) calculations with the PDC bits, and we changed PDC bits to see which cutter depths gave us the best penetration rates. MSC calculations consider weight on bit, torque, RPM, and they haven't been used in geothermal very much. They are used somewhat in the oil and gas industry, but they prove to be extremely useful. Well, 5832 is shown in green, and that was the first well, and that was drilled with trichome bits. Okay? We sort of averaged something like 4 meters an hour, and what was that? 4 meters an hour and maybe 40 hours on a bit. Okay. The blue dashed line was what we predicted the 16A well would take to drill. We predicted about 140 days. We drilled it in about 80 days or so. A little longer than that. So very, very successful using the PDC bits and MSC. We were able to even to increase drilling rates in the 56 well. 56 is shown by the red lines, predicted footage and days is shown dashed. And again, we basically doubled our penetration rates. In fact, from what we understand, according to NOV or Reed Hycalog, who provided the bits, we set a record of 1,208 feet or 368 meters in 53 hours with an average of 25 feet per hour. The reason this is significant is when drilling wells for power plants and building power plants, drilling accounts for approximately 50% of the total cost. And so anything we can do to reduce the cost of drilling will result in very, very large savings. So at this point, this is one of the main important takeaways from the project. Okay. One of the reasons that the DOE kind of settled on this 175 to 225 degree temperature range is because it was thought that we could utilize oil and gas technologies, oil and gas tools. Okay. I'm going to speed up a little bit. Prove that this wasn't quite true. You can see here failed packers and bridge plugs, damaged jars, a worn trichome bit. It turns out that we've had about 95% failure rate on the tools that are routinely used in the oil and gas industry. Much of the information that we've collected so far has come from 5832. The well and all future wells were extensively logged. We've performed diagnostic fracture injection tests or injection tests, and we've run full suites of logs. Okay. FMI log is proven to probably to be the most useful of all of the logs that we've run. The center is an FMI log with a vertical fracture shown by the dark line. And you can see it waves a little bit as it intersects natural fractures. Okay? We assume that vertical fractures in a vertical well are induced fractures. Okay? And these are shown by the green stereo net. It indicates that the strike of these fractures is northeast. Because of the strike, we assume that the maximum horizontal stress is also northeast. And to take advantage of the in situ stress field, the deep injection and production wells are being drilled perpendicular to it, approximately from the northwest to the southeast. The blue histogram shows natural fractures. There are more than 2,000 of them in well 5832. Dominantly, they dip moderate angles at about 60 degrees to the west. Despite the large number, permeabilities are very, very low. There were no mud losses or gains during drilling, and the permeabilities are on the order of about 30 microdarcies in the granites. Several stimulations were conducted. some in 5832, and then in 16A. We stimulated the open hole, then the cased hole, and we stimulated regions that were had numerous critically stressed fractures. These are fractures that are ready to slip under low pressures, and they're shown by the red discs in the figure on the right. And then we did an open hole stimulation in 16A. The breakdown occurred at the surface in the open hole at low pressure, and in the cased hole section, we also were able to stimulate critically stressed fracture. The figure on the upper right shows the classic breakdown in terms of time and pressure of a fracture zone. And on the lower right, we see microseismicity during the stimulation. We only had one well to monitor, so locations are not accurate, but we were able to document many microseismic effects. We also tried stimulating a zone that had few fractures, and unfortunately, the packer failed, and we were not able to stimulate that zone. Okay. Beginning this year, and the next 2 years or so, we will drill several other wells. Wu 1 will be a well of opportunity. It will be 3,000 meters deep or so. It will contain a DAS cable deployed and cemented in the annulus of the production casing. It'll be 7-inch casing, just like the 16A. And this will be primarily for testing tools. We'll drill 16B, which will be the production well parallel to 16A. And then we will drill Wu 2, well of opportunity 2, for additional tool testing. Give you some sense of the timing. Wu 1 will be drilled within the next 2 months. In the end of summer, fall, we will stimulate the open hole section and 2 case sections near the toe of 16A, and deploy geophone strings in the 3 deep wells to monitor seismicity. In 2022, we'll drill 16B, and then later in that year, stimulate 16A and B. We're not sure what the stimulation program will be. It certainly will be in cased hole, and we may stimulate both up and down. We're currently working on stimulation programs. And then in 2023, we'll drill the second well of opportunity and initiate the long-term circulation test. The project is scheduled to end in 2024, but we anticipate the Secretary of Energy will continue the project for another 7 years. In conclusion, the granitic rocks have appropriate temperatures, low permeabilities, and stress orientations for EGS development. The injection tests demonstrate that critically stressed fractures can be stimulated at quite low pressures and injection rates. There are no endangered animals or fauna. Groundwater is not drinkable, it's not potable, it's not utilized fully, and it's not fully allocated. We have millions of gallons of water per year allocated to the Forge project, and there is relatively low risk of induced seismicity and seismic hazard. All of the data I've discussed and all of the data that will be generated by the project is publicly available in the Geothermal Data Repository. Here's their website. You can find Forge data on it. You're welcome to use any of it. We simply hope that you will acknowledge the Forge project for providing that data. And finally, I just want to thank you for your attention. I'm pleased that I was able to speak to you this afternoon. Happy to take questions. If we don't have time, email me And I seriously encourage you to get on our website, see what we're doing, follow us on Twitter and Facebook, see our videos. There are 5 YouTube videos out there at this point. So I thank you for your attention.
Thank you very much. Very, very interesting, fascinating presentation. Vasiliki, are there any questions raised so far?
No, we don't have any questions at the moment.
Okay. As we are a little bit short in time, Joe, will you be with us until the end of this? Or
I'm
you have
going
to
to
leave
try.
earlier?
I'm going to try, but I will
Okay.
be, if I can't stay the entire time, I will be back.
Okay, okay. Because I would
Beforehand.
have some more interesting questions, but I'll try to put them in the end at our discussion round then, and we would
Very
in the
good.
meantime go proceed with the next presentation.
Thank
Okay.
you.
Thank you very much. And I will now share my screen again, and I would like to welcome the next speaker. So does it work? Yeah, here we go. So Albert Chandet from Geothermal in France will now speak about operational experiences with EGS in France in the Rheingraben. And I'm very happy to have you here today. And I'm very interested in your presentation. So Albert, the floor is yours.
Okay, thank you very much. I will upload my PPT if I can find it. In fact, I don't see my file. Yes, I have it. Let me know.
Yes, we can see your screen. Perfect.
It's full screen, it's okay?
Full screen, yes.
Okay, so maybe I will switch off my camera, maybe, or I can keep it. Anyway, so first I would like to thank Gregor for giving me the opportunity to report about our ongoing project in France, operational project. And on the behalf of my colleagues, my co-author, I will try to summarize some main findings we have on 2 operational plants we have in eastern part of France. I also take the opportunity to say hello to Joe Moore, I know quite well, spent some time in China with him, and also Dejan, I know quite well from University of Belgrade. So thanks to those gentlemen and the people who are following those talks. So first, before starting, it would be clearest for you to know who we are. We work in eastern part of France. Our company is ES, meaning Électricité of Strasbourg, so one of the main cities in this area. And it is our mother company. And our mother company invests and develops some projects. And personally, with my team, we work in a subsidiary of ES. The name is ES Geothermal. We have roughly more than 20 people, and we have 2 plants. We are responsible for maintenance and exploitation, and also we have scientific and technical staff, expert in deep geothermal energy. So we are in the real life because we have plants, operational plants, but we're also deeply involved in some national or European project, and I will show you some main results, for instance, from the MIT project, which is a Horizon 2020 European project we are coordinating. So I will speak mainly on those 2 sites you can see here, Soulsous-Forêt, which is quite famous because we start more than 30 years ago by, I would say, scientific, and then a pilot, and then now it's an industrial project. Rittershofen, which is another project we did some years later, more industrial. We are less than 10 kilometers from Souls. And there is another name here, which is Banheim, close to the Rhine River, close to the German border. Banheim, it's not the name of the project, but it's the name of the factory where the factory is located, because we are selling heat with Rittershofen, we are selling heat, and with Souls, we are selling electricity to the grid. So I will explain more in depth those 2 projects. But generally, as we are working in geothermal energy, what are the main questions we are talking about? Our concern is to produce the highest thermal power. And how to improve the thermal power? We can play on 2 main parameters. Either you try to improve the flow rate on this equation, which is M. So how we can increase the flow rate or the flow mass? We can do it by doing various kinds of stimulation. So first point. And the second thing, when you're doing a geothermal project, you are pumping hot water and re-injecting colder water because you're taking the calories. So generally, you cannot improve the temperature of a site. So you can play on the re-injection. If you are able to re-inject at lower temperature, you can produce more energy. And it's exactly what we are doing in the framework of this MIT project. We use the soil site as a demo site because you see on the sketch on the bottom, we are roughly producing temperature at 150 on surface. We are taking the energy, producing electricity, and then we are reinjecting in the reservoir at 70 degrees C. But thanks to the MIT project, we have added some small ORC unit. I will show you some slide later, in order to produce a lower temperature. And in that case, we are increasing a bit the thermal power. So it's a research project. The idea is to produce more energy with the same infrastructure. So it is our challenge in geothermal energy, whatever the kind of geothermal energy, is to produce more thermal power and then doing either heat, either electricity. So generally, in our case, it was presented by Gregor in the main introduction. In our case, we are always, there's a kind of continuum between hydrothermal system, which is quite classical, like in volcanic area, for instance, or purely medium, which have no permeability at all, called petrothermal system. In our case, and we are working in the Upper Rhine Valley, eastern part of Europe, we have, I would say, many natural fractures in this area because it's tertiary grabens, and those fractures, natural fractures, have been reactivated by a series of thermal, hydraulic, or chemical stimulation. And then we are going from low permeability to higher permeability. And I will show you what we did at Source and Rittershofen briefly. But generally, stimulation is only the first step of our system because we increase the flow rate. But after, we have to permanently circulate it in this project to produce electricity. Stimulation is some days, sometimes some weeks, but days. Circulation and exploitation is weeks and months, years, and sometimes decades. So we need to keep the flow rate permanently in order to produce energy during all the year and generally for more than 2 decades in the framework of the French, I would say, mining code. So if you look at the sketch at the bottom, in our case, based on many wells we did, what we learned that even in a very hard rock like granite, which is reputed very dry, very tight, we find water, but generally not enough for commercial and economic projects. So we were obliged to do stimulation and various kinds of stimulation. And we demonstrate based on tracer test that the system is open. And then we are, at the end, we drill some production well. We put a pump in the well in order to have industrial flow rate. We are taking in surface the energy, and we are re-injecting all the water in the reservoir. And in that case, we have no emission, zero emission, for instance, in terms of CO2. And then a part of the water could be, I would say, reheat, but also as we are an open system, we have no decline of the production versus time. So, and also one thing which is quite important in our case, we speak about EGS not only because we are doing stimulation, but we speak about EGS also because by reinjection, we can also trigger, generate induced seismicity, and then we have some hydromechanical phenomenon in the reservoir, and we are measuring this induced seismicity during exploitation. And for us, it's I would say also a part of the name EGS. EGS is stimulation for improving the well, but it's also EGS because you are permanently re-injecting all you are producing, and then you have hydromechanical process, mainly at the re-injection side. So here you have a slide of our two plants we are operating. So on the left, you have the Soul site with the main, I would say, feature, the main characteristic. We have fractured granite, which is quite old. It's not tertiary granite like in Utah, but it's, I would say, a carboniferous granite. One thing is also we find in those granite, we find brines, very salty water, 3 times the seawater. You see 100 grams per liter with a lot of species in solution, and mainly sodium and chloride. One thing also which is interesting for the future, we find also quite a great quantity of lithium in those brines. And for source, we produce 1.7 megawatt electricity from some deep wells. And you have the main feature, which are the flow rate and the temperature on surface, which are here notice on the left. For Rittershofen, which is a more industrial project, we learned by drilling at source that we are not obliged to drill at 5 kilometers deep to find permeability even in the granite. And then we divide by 2 the depths of the wells in Rittershofen. As you can see, we drill roughly to 2.5 kilometer deep vertical, and we are able to produce more flow rate. In fact, we also did stimulation on one well, I will show you, and we improve the flow rate in a maybe more efficiency. And then we produce more flow mass and higher temperature, so more energy. And here it's a heat project, not electricity project, but a heat project. We are selling the heat, and we are producing roughly 24 megawatt thermal. And also the same kind of, I would say, brines, and also roughly the same kind of lithium, which is dissolved in such fractured granite reservoir. But we are not alone in this area. So you have here, I would say, a sketch of the geological map of the Rhine-Graben, which is between Switzerland, France, and Germany. And the two plants at the bottom of the slide are the Sulz and Rittershofen. I will go more in depth, but there are other sites like Landau and Insheim. It was mentioned during the speech of Gregor also. Those sites are also producing, I would say, some energy from also a reservoir, which are in EGS reservoir from this area. So there is a real, I would say, development in this area because all those projects are operating and producing energy, either electricity or the heat, either both. So now some focus on the Sulz site to go more in depth on this site. So as I already mentioned, this site is located in the Upper Rhine Valley. It's a graben area. So one thing which is interesting to notice, it's a non-volcanic area and there is no hydrothermal manifestation on surface. There are some spring like Baden-Baden or things like that, but we are not in Iceland or some country like that you have a huge, I would say, fumaroles or thermal springs. So it's, I would say, the volcanoes are quite old, and then it's not a typical volcanic area. We are looking with unconventional reservoir, granite, which is not reputed as permeable. So it is in terms of location and reservoir. The technology, we drill several wells. You can see a sketch at the bottom. We drill a series of wells. One is now was considered as an exploration well, GPK1, black on the section, and we have one production well, GPK2, with a pump, with a line shaft pump inside, and 2 reinjection wells. The wells are vertical till roughly 2.5 or 3 kilometers deep, and then they are strongly deviated. And then the horizontal distance at the bottom hole of 2 consecutive wells is roughly 700 meter lengths. So the site, we have sediment, because we're in a graben area. We have sediment on the top, at Sulz, roughly 1.5 kilometer thick. And then after you have the basement, which is mainly a granite. On this site, we have we install a ORC, meaning organic Rankine cycle unit. And also we benefit from the French feed-in tariff, you can see, which is 246 euro per megawatt-hour. It's the only site in France producing electricity from basement, from EGS. There is no more, and we got that we call a concession. Then we have the right to exploit this site to 2040. But on this side, we have no heat application, because, and as you remember, I mentioned that we are ranging at 70 degrees, is the reason why we try to see if we can produce more energy or to find interesting heat application to exploit more the thermal spectrum of the site. So we are on the highest geothermal anomaly in Western Europe, as it can be seen on the thermal map, temperature map at 5 kilometers deep on the top left, on the top right of the slide. In terms of temperature, we notice that we have several, I would say, thermal anomalies in the Graben, which are known from the old oil field, I would say, history. And generally, those thermal anomalies are clearly related to fault, fracture zone, normal faults, structural faults. So the fault system is controlling the thermal anomalies. And what we learn also that there is a link between the permeability, fluid circulation, and those thermal anomalies. And also, by drilling, we discover that the fracture system, which is roughly vertical, is quite permeable after stimulation in the granite, but also we have some evidence of permeability in the sandstone, in the Budenstein, in the Muschelkalk, limestone, which are two Triassic sedimentary layers, meaning that the fracture system is vertical and cross not only the granite, but also propagate upward into the overlying sediment like Budenstein and Muschelkalk. Also, we evidence a feature which is quite important, that around fractures, we have strong hydrothermal alteration, meaning that there are some in the past, or maybe now, some strong water rock alteration, that the rock, mainly the granite, is dissolved and act also close to the fractures as a dual medium between matrix and also fracture system, and then could explain why we have local circulation into the granite. So this is a thermal regime we observe at source. So you have a thermal profile. So on the verticals, you have the depth between 0 and 5, roughly 5,000 meters. And on the horizontal axis, the temperature between 0 and 200. We measure in the 3 deep wells at source, which are reaching this deepest temperature of 5 kilometers. We measure 200 degrees C at the bottom depths. But as you can see here, the thermal profile is not a straight line. There are several, I would say, parts in the thermal profile. The upper part, which is mainly in the sediment, show a very high thermal gradient. You have the number on the left. So you have at 1 kilometer, you have more than 100 degrees C, which is probably the highest temperature zone in France in the first kilometer. But as soon as you reach the brittle rocks, mainly the Muschelkalk or the Triassic, the geothermal gradient drops a lot, and we can see, as it's shown in red, when you cross some permeable feature, you have a kind of convection, meaning some local small slow circulation into the fracture system, and then you homogenize the temperature in the intermediate part of our system. And at good depths, again, the thermal gradient become again more linear, more conductive, and we have less permeable feature at good depths. So we have a real conductive network, convective network at the top basement. And it's the reason why when we drill Rittersofen, we decide to hit the fault in the granite, but in the first kilometer of the granite. So it was mentioned also by Joe before, for improving the rock, because we have low permeability, we did some hydraulic stimulation. And when we did hydraulic stimulation, we had also some induced seismicity, as is shown here on this plot. The gray chart on the left show you the density of induced earthquake during stimulation. The red curve shows you the pressure, the overpressure on surface, and the blue curve show you the flow rate. So there are some interesting features, even I will not go in details, but here, for instance, you have the flow rate of roughly 30 liters per second, and you can see, some, I would say, seismic crisis. For instance, when you change between 30 to 40 or 40 to 50, you have a lot of seismic event there, meaning that you have a reaction of the median, as it's shown on the right, with the cloud, seismic cloud, which is plotted here in 2D. So how it works? Somewhere you have some normal stress on the fracture, as is shown on the block diagram on the top. And because you're injecting some pressure and some water in the system, you minimize this normal stress to the fractures, and then the fracture open. And as soon as the fracture has less stress on it, shear a bit, or hydro shear, as it was mentioned in the slide of Joe, and then you generate some induced earthquake. If you stop the injection, for instance, here, if you stop the injection, in fact, which is quite tricky, is the pressure is not coming back to zero, so to the axis, but there are still some energy in the system here. And you can see that even if there is no more flow rate, we stop the injection, we still have some earthquake here, even a low, I would say, a low frequency, but the largest earthquake we observe in Souls, in Petrothermal, but also in Basel or other sites, got the largest magnitude, and sometimes they were felt after stimulation in the shutting period. So what we learn at Souls, it's in some case, by hydraulic simulation, this one was done in 2000, we could have some earthquake, we could felt, magnitude maximum was 2.9 during the shutting period. So so I show you some results during stimulation, but now during exploitation. So I show again the same plot on the wells. You can recognize the well on the cross section, and here I summarize what happened, for instance, 2 years ago, but it was the same last year. During 1 year, during exploitation, so we are permanently, because the plant is the availability of the plant is quite large, more than 90%. We are measuring permanently the seismic event, and about 1 year we have less than 50 events, and the maximum magnitude was 1.3, low PGV, low peak ground velocity, and most of the events are located to GPKS4 or injection well, meaning that nobody felt any earthquake during exploitation, and this exploitation started more than 5 years ago. So the message is you can exploit the site without any trouble during exploitation. In the framework of MIT, we try to do more energy with the Soul site, and I already mentioned that we are producing at 150, we're injecting at 70, and now we start 3 weeks ago a new test on site. We install a small ORC unit, which is there on the screen on the green and the box and the shelter, the green shelter. We have a new ORC unit. It's a mobile ORC done by Energia, our partner, and we try to produce more energy by re-injecting at lower temperature, lower meaning 40 degrees C. But today we are not at this temperature, we are close to 60, but we try to see if we are able to produce more electricity on the same time, just by adding, I would say, new technology, and then having a more thermal spectrum and more energy from the site. But when you're doing that, if you are injecting at lower temperature, you could have some problems, some challenges. For instance, you could have some natural radioactivity. So how? You remember we are on the granite rocks, and then we could have scalings, deposit, because at low temperature we have some minerals which could be deposit, and then so we have to monitor, for instance, also the natural radioactivity on site, which is one of our purpose. We could also induce seismicity. So I already mentioned we manage induced seismicity permanently, and we can also have some problem in the wells, some corrosion, some also problem with the pump, and so on. So we are working on those in parallel to the fact to produce more energy. We also working on different, I would say, technical and scientific challenge during re-injection at colder temperature. Now in few slides, recursive on site. So you can see a nice picture of the plant, which is 6 years old, and which is also operational. So this site, in terms of, so you remember, we are less than 10 kilometers from source. In terms of reservoir, our target was a local normal fault in the basement. Those colors correspond to the sediment. We are the top basement, and then we target this fault during drilling. So this project is a HEAT project, and there are 3 main, I would say, investors: our mother company, and two other one, Rocket and Caisse des Dépôts, so two other French company. And in fact, this project, the aim of this project is not to provide electricity, but to provide heat to a big factory. It's a biorefinery, which is located close to the Rhine River here, and which has a big needs in terms of heat. You see, roughly 100 megawatt thermal, and based on the geothermal project, we are able to produce 24 megawatt thermal. And if you see a sketch of the site, we have two wells. I will explain later. We have a transport loop, which is below the underground, which transport some water which have been overheated through the heat exchanger and to the factory of Banheim. And there are various, I would say, processes of biorefinery from vapor to colder, and then the cold water is coming back to the geothermal plant through a pipe for again taking new energy and going back to the factory. So generally, people ask us why we drill in Rittershofen and not close to Banheim to avoid those 15 kilometers away of transport loop, which were very expensive. Why? It's because the geology. If you look on this very simple, I would say, block diagram, we hit the top basement, so more or less our target, at roughly 2.2 kilometers deep in Rittershofen. If we have to do the same below the factory, because we have a graben system, the top basement could be at 5 kilometers deep, meaning higher drilling cost, maybe more earthquake during stimulation or operation, and so more risk. And so we decide to drill here, and then to get, I would say, the resource instead of to take many risks close to the factory. And because to drill horizontal well at 1 meter deep in the ground is not a big technical challenge. It's more challenging to reach, I would say, at 5 kilometers deep, some geothermal resource in the Rhine Graben. So the site, in a few words, so you have the technical design of the site. One well is vertical, his name is GRT1. The second well is deviated, GRT2. So the two wells are in operation. The first well was stimulated. I will come back to that. And the second well was not stimulated. So it has been classified as EGS because we conduct thermal, chemical, and hydrothermal and hydraulic stimulation. And I will not read again, but it was the same, more or less the same feature we have at source, the same granite, fractures, and also a kind of fluid we find in this site. So in Rittershofen, when we drilled the first well, the productivity index was quite low. It was 0.5 liter per second and per bar, and then it was not economic. So we decided to do first a thermal and then a chemical, focus chemical stimulation, and then hydraulic stimulation. And by doing that, we have induced seismicity. So we had induced seismicity with thermal stimulation. We haven't any induced earthquake with chemical stimulation. And again, we have induced seismicity when we conduct the hydrothermal stimulation of the first well. And you can see on the plot, on the map, on the cross section, the cloud of the stimulation when we did the hydraulic stimulation mainly of the wells. So first result, nobody felt any earthquake during those operations, and the highest magnitude we had was 1.6, and it was, I didn't show the plot, but you can find it in Bojar et al. In Geothermics, it's online. We have this 1.6 magnitude earthquake during the shut-in period, so some days after the end of the hydraulic stimulation. The second well, when we drilled the second well, the deviated well, GRT2, it was so good that we don't need any stimulation because you can see the productivity index, it was higher than 3 liters per second and per bar, and then it was decided to make an industrial project. So in terms of after simulation, we have operation. So in terms of operation data, this is the data from last year. I can mention that the well head temperature is very stable at 168 degrees C. The average production is close to 300 cubic meter per hour, which is a high rate in granite. We have only 2 weeks of maintenance per year, roughly. So the availability of the plant is very high, higher than 90 degrees C. And then you can see the amount of energy we are producing per year, 180 gigawatt hour of heat, and we sell this heat to a factory. And then we are selling also CO2, which is quite important. And also one information which is interesting, we are not losing so much temperature between the plant and the factory, because we lose only 4 degrees between the wellhead and the heat exchanger on surface, and we're overheating fresh water to the factory, and we are losing again 4 additional degrees. It means that the hot water arrives 15 kilometers away from the wells at 160. So it's a very good and interesting temperature with a high flow rate. So as a conclusion, so the message is we spoke about EGS in the Upper Rhine Valley because we are stimulating and reactivating existing fracture system, which is generally sealed by hydrothermal product. I mentioned strong hydrothermal alteration, and generally we are doing stimulation just after drilling operation. And it's very rare we are doing stimulation during exploitation. We did once during a research project. It was distress, but generally we don't need to stimulate again the wells. It has been stimulated after drilling, it's enough. We observe, and it is a bit tricky to speak about petrothermal of EGS, we observe some fluids. There are natural fluids. The problem is to try to hit and to collect the fluid, because generally the fluid is circulating in channels which are difficult to find from the surface. And then the big challenge is to drill and to find those permeable features, or at least to find the right way to stimulate them by minimizing all the, I would say, the environmental impact. We know also that the fractures is also permeable in the sediment, but probably less. So that means the Bunsenstein and the Muschelkalk. But in terms of, so it's mainly what we learned from, I would say, exploration and stimulation. From operation point of view, we demonstrate that we have no felt seismicity during exploitation on the 2 sites we are operating now commercially for more than 5 years. They have very good availability, meaning that the plant, or either the electricity, either the heat plant, are working very good. But maybe you heard that in Strasbourg there are other geothermal projects, deep project, EGS project, and there were several felt seismic events, and because of that, now the prefect, so the mining authority, stopped all the projects, not Sulz and Rittershofen, but they stopped all new projects. And then we know that in the future we will need to communicate a lot and to explain a lot how works our technology, because, for instance, we have earthquake today, but they are very low, nobody tells them. But we need to, because of that, we have a strong problem with acceptability, and then we have a lot of work to do. But I would like to mention that in the Upper Rhine Valley, and at least in the area where we're working, we know there are potential for other projects, maybe not in the Strasbourg area, but close to Sulz and Rittershofen, there are plenty of room for doing new projects and to produce more energy, maybe also to produce lithium, to do greenhouse and other application. And then I hope we'll have a future for developing EGS in this area of Europe. And then thank you very much for your attention, and I'm happy to answer a question or comment.
Thank you very much, Albert, for your very interesting talk. My question to Vasiliki, are there questions from the audience?
Yes, we have 2 questions from you mainly. So, is the magnitude of induced earthquakes the limiting factor for the ejection rate in Sulz?
Sorry, it's not. Please speak loudly because I cannot understand.
Yep. I can because it was my question. Vasiliki, your microphone has problems again, but I will ask this question. So the magnitude of the induced earthquakes, is it a limit, or was it, or is it a limiting factor for the production or injection rate you apply in Sulz and Rittershofen?
No.
Could you inject more, but would then expect higher, stronger magnitude earthquakes?
So in fact, we are injecting what we plan. So 30 kilogram per second in source and roughly 300 cubic meter per hour in return soften. And sometimes we're injecting a bit more because the well is very, GRT2 is very permeable. So we are not, in terms of magnitude, we are happy to observe those magnitude, but we really, I would say, we are doing what we sell to the investor. We sell those flow rate post stimulation, and then we are perfectly in line. One thing I did not mention, maybe for your understanding, I did not mention the overpressure on surface. We have quite low overpressure, both in source and return soften. Today, we are operating the site with 25 bar maximum, so 2.5 megapascal. So it's a very low pressure, I would say. So the wells, we have low pressure and also in return soften. If you look the paper of Bojar et al. In geothermics, the maximum wellhead overpressure well was 30 bars, so 3 megapascal. So we had low pressure during stimulation and we have very low pressure during exploitation. So we are not, and we are not observing, I would say, increasing of magnitude. Maybe what we are increasing, it's sometimes we have much more, I would say, induced seismicity frequency in return soften, probably because the flow rate is higher. But in terms of magnitude and PGV, now we are not speaking for the French regulation. We are not speaking anymore in magnitude. We are more speaking in terms of peak ground velocity because it's a physical measurement, and we have quite low peak ground velocity either in source and either in return soften.
Okay, yeah. There are further questions. Maybe I would like to keep them for the discussion round because we're a little bit advanced in time. Maybe also in the meantime, if you like, Albert, feel free to answer the questions also in the chat. But I will pick some of them up in the discussion. So
no problem.
Thanks a lot for the great presentation. And I would now like to, move forward to the next, let's say, research site in Europe or future research site in Europe on enhanced geothermal systems. So I would like to invite Antonin Tim from the University of Prague and Geological Survey of Czech Republic to speak about the Litoměřice project on the border between Czech Republic and Germany. So I hope, Antonin, you're here because I switched the order.
Well, yeah, I'm here.
Okay, great.
I'm just hiding behind the admin name. Sorry for that. It just happens when the hands are quicker than the brain. So that has happened to me actually. So yeah, I will share my presentation. Hope it works properly. Can you see it now?
Still okay. You see the presentation, so you can proceed if you like. Just tell me to click.
Okay, I can't see it right now, but that is just because probably my slow connection. Anyway, okay. So my presentation will not be so scientific because I would like to present what we have achieved so far in terms of preparation of EGS project, and currently we've got only one well, 2.1 kilometer, which has been recently turned into a monitoring well, and that's all actually what we have. So we focused last 10 years or more than 10 years for really preparing ourselves for such a big project as, for instance, in Susufore, which was an example for us and still is. And so I would like to give you a short overview of the state of the art actually and future prospects or our plans. And hopefully this can be also start for cooperation with some of you and your institutions. Actually, we have been cooperating for a long time with some of you already. The first slide, if we can move to the second slide, the general overview. So, and maybe we can turn into to the third slide already. So at the beginning, just a short summary, and maybe I would say that our project is also quite interesting in terms of Czech Republic, because there is a huge need in terms of transition from the fossil energy to renewable energies, and we've got more than 2,000 DHS systems, district heating systems in the Czech Republic, which work under 5 megawatt hours, and for these district heatings, we believe that the geothermal EGS source will be very suitable to replace the coal, which is the major source of energy. However, currently there is no EGS or HDR project in the country, and the Litoměřice project is actually the first attempt, and this is probably something different from the other projects, as at the beginning was the city, which in 2005 had a journey organized by World Bank and going to Landau and Susufora and other places that have been mentioned already. And with this inspiration, they decided to develop an EGS project in the city. There are several other potential locations. However, there is very slow development, and we only work on exploration, the potential in terms of licenses and suitability for the EGS or HDR project. There is quite like a legal framework for geothermal sources. There is actually no geothermal legal framework currently, and we have to follow other usually minerals or hydrocarbons mining procedures to get the license. Anyway, we've got a license, which is a great thing. It took us 3 years to get it. And we face currently the other barrier, which is the financial barrier. So there is no national funding scheme, and we are depending on the EU funding and other external resources. And one of the institutional barriers is also that the renewable energy resources in the Czech Republic are in some way quite unpopular due to past failures in terms of huge subsidies, and now it turns into higher prices for electricity. Anyway, we hope that, and we already submitted a few projects, and we hope we will submit our major project worth of 60 million euros next year, because there is a huge funding scheme called Just Transition Fund, which is actually intended for these coal regions we are part of. The slide number 4 shows only a couple of localities. We are in the locality situated in the northwest of the country, with the biggest pink or violet stain, let's say. And as you see, we've got a couple of other localities. However, they are competing with with spas actually, and other use of the hot water. So the pilot Litoměřice EGS project started in 2004, as I mentioned, but it was quickly quite clear that the city cannot lead the project alone. So in 2014, they actually started a cooperation with the scientific community, and since that time, the Charles University and Czech Geological Survey were the leaders of the project and developed the research infrastructure I will talk about a bit later. So we believe that we will end up with a successful project, and also because in 2026, the district heating system located in the city has to be replaced. Coal has to be replaced by another cleaner source. So which you can see on the next slide, moving towards decarbonization. So we've got district heating system supporting about 70% of the total heat energy or thermal energy distributed generation, and we will, our aim actually is to replace it with a cleaner source, and hopefully this will be the EGS source. Another slide shows you the greater success. I would say you got two. So this was the first one. So during the first exploratory well in 2006 and 2007, confirming the thermal gradient, and we got quite a lot of data, of course, and about the lithology and about the general geological area. And that was actually the key point for the city to decide to go on and strive for the real major EGS project. We've got actually 3 different phases of the project. The phase 0, as we call it, that was the phase when the city was the leader of the project. Since 2013, we as scientists and academics, we took over the project, and in the first phase, we developed the research infrastructure called RINGEN, which is the acronym for Research Infrastructure for Geothermal Energy. And we started in 2016, and in 2020, we finished building this research center in the city, and we actually created a great platform for the research and applied research and development in terms of geothermal energy, or as we call it more broadly, geoenergy, because we want to also promote the underground thermal energy storages in combination with the deep EGS project. The phase 2 on the next slide, it's called application of EGS. So after the initial phase, we would like to drill deep, 2 deep geothermal wells. And as I mentioned, combine it with also underground thermal energy storages using depth of between 100 and 1000 meters. So this is quite challenging, of course, but there is a great support from the city, and they dedicated an area of some 3 to 6 hectares actually for scientific purpose and it's a development site. And we would like to follow the Sulzufore example and combine research and generation of heat. The third phase on the next slide is of course operation of the EGS source, but this is quite far away from now. But this is a plan, and then work as an example. Actually, everything what Albert Jante already mentioned. So provide data and be a pilot project for not only hopefully Czech Republic as we work in the metamorphic rocks of the Bohemian Massif. So this is quite unique or not so developed geological structure. So we would like to be a testing site and develop further and hopefully achieve broader use of geothermal energy in the Czech Republic. The next slide is a short summary of the current state. And that means where we are. So you see that the basic research is more or less done, but we still have lots of to do, and we've got small projects focused on seismicity or mini fracs testing and injection test in the current well. We've got suitable locality, as I mentioned, and great support from the city. We've got all the licenses we need. We constructed the research center itself, and we've got about 60 to 70 researchers from 9 leading institutions are dealing somehow in some aspects with geothermal energy. And we also cooperate very intensively with the international community. We do have also support of the local community in terms of general public, and we've got great business partners. The greater one is the company which operates the district heating system, which is actually part of the German MVV company, and these are very helpful and waiting really for our results and want them to accommodate them and use them for their business. And as I mentioned, there is a transition of the region from really coal-based energy to renewable resources, and there is not enough water or hydro sources or energy or wind sources. So and solar sources is very limited in terms of space. So geothermal sources is one of the really most promising source in the future. What we are missing are the funding opportunities. So the last or the next slide is about the Ringen itself, but I will go through it very quickly. So as I mentioned, we are 9 leading institutions. So you see that we've got the geothermal site, seismic monitoring network. We've got at disposal the exploratory well, and we've got a couple of other underground laboratories and facilities that can be used for testing of individual parts of the EGS systems. The next slide is about Ringen seismic network. There is already 9 stations combining surface stations and underground or borehole stations, and actually one of them is the former exploratory well, where there is the seismometer in 1.5 kilometers, which is actually the deepest borehole seismometer in the Czech Republic. So this is already set up, and we monitor background seismicity to be able then to distinguish between the natural seismicity or the industrial seismicity and the EGS seismicity. The next slide, this is just about other experiments I've mentioned already. So we did some hydraulic tests on the borehole, and we want to continue this and next year just to get more data for the major project. And there are a couple of pictures on the next slides of the research center itself. So this is how it was supposed to look like. The next slide shows the locality and in a greater context, and you see the building of the center. So this is related. This is all located in the former barracks area. So this is a brownfield actually formerly used by the Czech army, and now is dedicated to the research in geothermal field. The next slide shows you just the main research fields. So we've got 4 research fields necessary for any EGS project. So basically heat flow, thermal conditions, seismicity, hydrogeology, geological conditions, and of course many other cross-sectoral fields within it. There's only few pictures from the works we have done. We have cleaned the well last year or 2 years ago actually. We withdraw the casing string, which was down to the 1.8 kilometers, and now the borehole is accessible from some 900 meters until this depth. There is cased borehole, and we don't know actually how far is it accessible. Last measurements were done, and we reached 1.7 kilometers with our thermal probe. And there are some other pictures from installing the seismometer I mentioned, yeah, that's it. And last 2 slides or 3 slides, I mentioned cooperation. So you see on the next slide the map of our partners. So there are 9 partners in the Czech Republic, but we've got many partners around Europe, including Geoforschung Potsdam and ETH Zurich, OST Strasbourg, and others. So the last 2 slides are about the future prospects. So the first of it is the slide showing the energy transition of the city. So this is a plan. You see the building of the research center. We'd like to combine it with other renewable resources using, for instance, hybrid photovoltaics, generating not only power but also heat during the cooling. And I mentioned the UTES systems and the district heat connection to the district heating system. And the main goal for the city is to be more or less energy independent and CO2 neutral if possible. And the last slide is about the locality itself. So you see that there is the Geoenergy Ringen Center. There is marked blue, and the yellow part is intended for new developments, including, for instance, hydrogen generation. And we also would like to popularize the geothermal energy sector. So we starting to develop geoscience area, basically focus on geosciences and how to use the geoenergy in a good way and to be aware of it. So that was really quick overview. So hopefully you survived until now, and I thank you for the attention, and we'll be ready for any questions. So thanks again, Gregor, for inviting us and giving us this opportunity to share our activities with you. Thank you.
Thank you very much, Antonin. So very interesting presentation. Sorry for the technical inconveniences, but I tried to follow as well as I could your talk with my slides. Sometimes I was a little bit behind. Sorry for that. So Vasiliki, questions from the audience?
No, we don't have any questions from the audience.
Okay, I just saw that there was one comment by Regina on funding opportunities.
I didn't. I cannot see it. Okay.
Okay, no, I open it. So Regina asked about if you already secured the just transition funding for your EGS project, because it also needs to be support of the Czech Republic.
Yeah, exactly. The region have to develop their own regional plans. That means the story they would like to about how they would like to use the funds. So that's underway, and we are among the so-called strategic projects, and in discussion with the regional government and with the national government. So hopefully our project will remain the part of the strategic projects, and this will mean that it will go and will be approved by the Czech government in September, and hopefully then approved by the European Commission at the end of this year. So that's the status.
Okay. Thanks for, yes, it was just on me. That's why you could not see it, Vasiliki. I just found it out. And I would like to ask one more question. So this is really a heating project with EGS, not a co-generation of electricity at the lithium. And what about the overall geothermal conditions? So is it also a high temperature zone, or would you say it's an average continental European conditions? You look at the geothermal gradient in the region.
Well, I will follow your slides, and I think it's something between the grade 2 and grade 4. So this is between, we target to about 70 to 100 degrees, but depending really on the conditions of the on the permeability or the rock formation, generally speaking. So the main point is to achieve a functional EGS source, and it doesn't really matter at this point if it's in 2 kilometers, 3, 4, or 5. I mean, of course, it matters in terms of money, but we will be happy to really have a working and functioning system generating some amount of energy which can be connected to the district system, because it's still a kind of quasi-scientific project or applied science.
Okay, thanks a lot, Antonin. I hope you also stay until our final discussion round. So we'll come now to the last presentation of today. So I'm happy to have Emilio Puya-Moyer here from the Spanish Geological Survey. We now go a little bit earlier to the process of exploration. And I'm very curious to learn more about your findings, your work in exploration outside of classic hydrocarbon regions. And the floor is yours, Emilio. So I'm looking forward to your presentation.
Thank you. Can you hear me, Gregor?
Yes, I hear you well.
Great. So first of all, I would like to thank you the opportunity to show us one of the actually concerns we are experiencing in the ongoing GeoEra project. So sometimes we need extra information for harmonizing, for building models beyond hydrocarbon regions. So this is the main talk of my talk. Let me see if I can. Okay. So this is basically the main goal. So illustrate or to show the exploration challenges in the earliest identification phases of a geothermal reservoir.
Sorry, Emilio, we cannot see your presentation yet. Okay, I'm ready to share. So I will share my screen. Just tell me next or click. Here we go.
Okay, go to the next one. And
here we go.
Yeah, okay. So the main goal is show the exploration challenges we have in the very early stages when we are identifying and doing an earlier characterization of deep geothermal energy reservoirs. In those areas which we have very few subsurface information, especially derived from the oil industry, and how to overcome them. So next, there will be two blocks. So the first one is trying to show the reasons where we have very limited seismic information or oil information, and then the how to overcome them will focus the second part of the talk. So next one. Yeah, oh, this is gonna be a mess because I have so many slices. Anyway, I mean, if we are talking about these early stages in the identification of deep geothermal systems, it's a matter if they are wet or dry rock, let's say so. And we are talking about regions with normal gradient, geothermal gradients. So we are necessarily talking about very high depths. So if you can go to the next one. So, and as we have seen from the previous presentations and current operations in Europe, most of the demonstration plants or production plants so far are ranging between 2,000 and or even 5,000 meters, like Schultz, as Albert told us. So all these early exploration phases in the geothermal energy has lots of resemblances with the oil industry. So by the end, we will need to characterize the 3D distribution of geological bodies and discontinuities in the subsurfaces together with their petrophysical properties. And because of this reason, I mean, these similarities are not only in the exploration phases, but also in production and monitoring and management of them. And this is why the big oil and energy companies has already turned the focus during the past few years, and most of them has already targeting and they're evaluating operations. Next one. One nice example is we can see from the Netherlands. So because the Netherlands probably is one of the for a country, one of the best subsurface data sets in the world. So they have a complete coverage of 2D and 3D seismic, onshore and inland. So for last years, they have already turned a lot to the geothermal energy. So 3 years ago, they have already 17 wells in production. So okay, they are not so deep like other examples that we have seen today, but I'm sure they have more than 100 wells in exploration right now. Next one, please. So actually, they have developed a very nice web interface called ThermoGIS that you can access if you want. And all of these outstanding subsurface data set is behind the system, together with some smart algorithms that allows you to, for example, take a look on the potential recoverable heat or the economic potential. Next one. But the problem is actually we don't have this kind of data sets everywhere. If comparing, for example, with the Netherlands or other oil fields. So the next slides, I'm going to show why we have some limited subsurface information. I will show examples from northeast Spain, but actually the lack of seismic information or wells may happen in many regions in the world. So next one, please. So I will first focus on the number one square. Next one. In this case, sometimes we simply cannot get seismic reflection because of the technical limitations. In this case, is the Snell's law. So in this nice example from the Western Pyrenees, we have a very large anticline with vertical limbs, and this, of course, precludes the application of seismic techniques. Next one first. Okay. Now, if you take a look in around square number one, you see there is no seismic at all, of course. Next two examples are squares 2 and 3. Next one, Gregor. So this exploration efforts done by the oil industry, of course, are controlled by the oil window. So those basins that don't have enough thickness to mature the organic matter, or even those basins at the other end member that they have too much thickness, and so in these cases the temperatures reached at the reservoir are too much high, and then the oil is burned. So this oil window totally control the exploration efforts that has been done by the oil industry. Next one. So first example comes from the westernmost corner of the Iberian Ranges in northeast Spain. There, in that basin, if you take a look in the restore image of the basin right at the end of the extensional period, we have actually two reconstructions of this. We may see that there are thicknesses from 7 to 9 kilometers, and thermometers has already evaluated temperatures above 350 degrees. So this means that there was no sense at all to do exploration here. Next one, please. So take a look in square number 2. There is a single seismic line in this basin. Now we jump to box number 3, which is actually, next slide, please, is the contrary situation. So in the central sector of the Iberian Ranges, in the northern part of it, we have very shallow Mesozoic basins, so many times not reaching 500 or 1,000 meters. And actually on top of that, we have very, very shallow tertiary cover. So all these conditions preclude, next one, preclude the oil exploration. I'm gonna show now the region just in between squares 2 and 3. Next one. Interestingly, so in between those regions, we have a couple of wells, no seismic actually, but a couple of wells which are very promising because they could be a nice geothermal hydrothermal reservoir. Those are buried naps by the tertiary cover in a breaking back sequence of the Iberian Range. Those naps are, we can find there permeable liassic limestones. We know from several studies that this is a regional aquifer, and these limestones actually have hydrothermal evidences at the surface. So there are some baths and hot springs, and this reservoir is about 2,000 meters at depth and could be a nice hydrothermal reservoir, probably. But we don't have any seismic information. Next one, please. Now we jump to the axial zone of the Pyrenees, where square number 4 is located. Next one, please. There we have another big problem that is happening in Europe in many regions. So in the case of the Pyrenees, we have lots of peaks and mountains above 3,000 meters, and many of them above 2,500. So this implies a strong relief and rough terrain that has precluded many times the seismic acquisition. Next one, please. Another problem of explaining the lack of seismic information are borders, political borders. So it's quite irregular that seismic surveys cross the borders. And imagine the situation in Central and Eastern Europe during the Iron Curtain period, because at the same time we had the boom of oil exploration motivated by the OPEC crisis. So, and not a single line there, seismic line is crossing the borders, and this is actually a big problem in the GeoEra network that we are facing using potential fields. Next one, please. So if we come back to square number 4, we will see, okay, in the axial Pyrenees, we have difficult access, so rough terrain. We have border limitations because of political reasons, except for the coarse seismic profile, which is quite relatively recent one. And actually, other regions in Europe, now here in the Iberian Peninsula at least, were not explored because were basement rocks, relatively complexly deformed, and complex geology in the Variscan basement. So those regions were not explored. So I really wonder how was the degree of information in Schultz. So maybe I get the answer from Albert later on. So all of these reasons converge there in the axial zone, and there is no information at all about the subsurface. Next one. Okay, and last but not least, probably, there is a quite frequent problem, even that you have the information, very frequently we don't have access to it. So this is an example from the westernmost Pyrenees. The upper square side of the rectangle has about 30 kilometers. So this coverage is not that bad. But when we started the project 3 years ago, we couldn't only access 50% of the sections. And from these 50%, only slightly more than 20% were digital files or SegWi files, and the rest was analogic files that were scanned at high resolution, but actually part of them were vintage, part of them were really poor quality, and from these analogic scan files, we don't have a real reprocessing possibility after that. So this is quite regular, that the information is there, but we don't have access because this normally seismic information is normally considered to be sensitive or strategic or whatsoever, or finally belongs to private companies. Next one, please. So if we take a look in one of the latest reports of the European Geothermal Energy Council, we can see that we have an asymmetric estimation of resources in Europe. So some countries has done very good the job, let's say so, but others, we can see some incomplete images, and even in the distribution of sites are very likely very inaccurate. And there are a number of reasons to explain this asymmetrical estimation of potentiality of geothermal energy, but one of them for sure is the bias caused by the seismic coverage. Next one. So how to overcome this problem? So I'm going to explain very well-known geological and geophysical approaches. So one of them is optimizing subsurface exploration using potential field geophysics data. So in particular, gravimetry and magnetism. And the second is using advanced 2D and 3D reconstruction and restoration tools. So next one, please. So remember that we are talking in the early stages of characterization of petrothermal reservoirs or deep geothermal reservoirs. So thanks, we have two potential fields in our planet, and it is well known for decades that the residual of these fields have really high value in the exploration of the near subsurface, let's say so up to 10 kilometers. So with the current sensitivity and resolution of the instruments we have so far, for magnetics and for gravimetrics, we may get really high resolution for these potential fields. Next one, please. So of course, we will be able to apply potential field geophysics if we have enough petrophysical contrast in the rocks underneath. So, but in our experience, we know very well that it's very rare that you don't have either density contrast or magnetic one. And if you are lucky, you may have both petrophysical contrast at the same time, which it will be much better and resolutive. Next one, please. So if you have this contrast in the rocks underneath, potential field geophysics are really a great technique and tool for harmonizing and modeling the subsurface, and actually is really quicker and much more cost effective. I mean, this is peanuts compared with seismic acquisition, and it's non-destructive, so you may apply even this in natural parks or preservation areas, and you may get really high resolution. Next one. Besides, one of the drawbacks of seismic exploration is easily tackled because of the current instrumentation for gravimetric or magnetic acquisition is really light. So you can take these instruments to the mountains. We did this in the GeoEra project, and if not, next one. You may use, of course, airborne geophysics, which after decades is really well developed and standard. And recently, we even may apply, at least for the magnetic acquisition, we may use drones, which actually makes the surveys much more affordable. Next one, please. The second way to overcome the lack of data, of seismic data or well data, is the use of subsurface reconstructions done from a structural point of view. So this is also very well known from the oil industry. Actually, they were responsible for the developing of the balance and restoration techniques for cross-section in 2 dimensions in the 70s and onwards. And for those that you don't know, these techniques are relatively simple. So means squeezing the information from the surface, honoring simple geometrical laws like the conservation of volumes, and also structural constraints from the geological point of view. And lastly, we can also use mechanical laws for the construction of this kind of balance. Next one, please. So all together, we represents a great tool for a great way for decision making in if we want to go ahead in the exploration of a geothermal reservoir or simply rule out. So the balance sections represent a top to bottom approach, and actually the potential fields data represents the other way around. So the residuals may inform us from the distribution of masses in the subsurface. So it represents kind of a bottom-up approach. So putting all together, for example, in Oasis, but there are several software platforms that we can run this balancing, and together with the petrophysical data, we can simply help a lot in the decision-making process. Next one, please. Yeah, if we talk about 3D restoration software solutions, the situation is different. So this is very likely condition because of once the oil industry got enough evidences for going further, they simply go for 3D seismics. And 3D restoration tools hasn't evolved too much comparing to other reconstruction tools. But in any case, there are three well-known solutions, and so far if the deformation is not relatively complex, they work very well. Next one, please. You can skip that one. Next one. Okay, so, but apart from this, we're working a lot on that is using platforms like GeoModeler or even the 3D plugin of Oasis Montage, because these kind of platforms allow us to merge all of the information we have from the surface, from the geological maps. We can integrate also there those sections that we have balanced for the gravimetric, magnetic, and geometry as a really tough constraints. Of course, we can do a 3D inversion of the entire data set. So this is an example for the from the southern Pyrenees. It's not a geothermal exploration. It was a salt structure, the focus of the research there, but it was very resolutive. And next one, I think, is the last one actually. So, and this kind of processing of the geological information from a probabilistic point of view, and the joint inversion with geophysical data with an structural focus. This is we are seeing this kind of research approaches to the subsurface in these regions where we have very little subsurface information, and we will see more in the future. So you may keep an eye on this project from Australia. We had a great seminar last week and I really promote this kind of modeling. The last one, please. So in conclusion, in the early stages of geothermal identification, in the identification of geothermal reservoirs, we may find these worst scenarios with a lack of information, and then for identifying them and doing a preliminary characterization to help in the decision-making process, we may apply quite successfully potential field geophysical data together with a structurally built 2D or 3D models. And that's all. Last one, and thank you for to the audience for all these technical problems we had, but by the end we were more or less on time. No?
Yes. Thanks a lot, Emilio, for your very interesting presentation. I mean, we could have an own webinar just on the content of your talk, and
yeah.
So I'm sorry for the technical difficulties, but I think we managed it quite nicely. Vasiliki, are there any questions from the audience?
No, we don't have any questions for Emilio.
Okay, I would like to make a comment to you. I mean, potential methods. There is an all cheap and cost-efficient way for exploration. I see always two problems. The first one is the resolution. I mean, but you couldn't be fixed via using drones and something like this, because the second one is the anthropogenic influences. So if you look at exploration close to cities, even if you're not in the classical hydrocarbon exploration regions, the magnetics might become difficult, I assume.
Definitely, but not gravimetric. So this is the
not gravimetric, yeah.
So this is not a problem for gravimetry. And the resolution strongly depends on the scale of your work, the density contrast, and the data that you made. By the end, it's a matter of budget. I mean, because even the data acquisition has a cost. So maybe, for example, in GeoEra, we acquire about 2,000 points. But if we would like to go further, then means more budget. But so this is a mixture between all these variables. But the key point is the density contrast or the magnetic susceptibility.
Yeah. Okay. So we come now to the last point of our workshop. Thanks for all still with us at quite late time now in the afternoon in Central Europe. So we come to discussion round, and I will we share my screen. And before I would like to initiate a final discussion. I think we still have a few questions, and I would like to give the word to you again, Vasiliki.
Yes, I have a few questions for Joseph Moore from Geomechanics Technologies. In your presentation, is it correct that the initial stimulation was performed in open hole and in the new well? And in the new well, you are switching to case stimulations. If so, what is the reasoning for that?
Okay. Thank you for the question. Can you see me, Silicon?
Yes.
Good. The stimulations in the first well, it was a 7,500 foot well, temperature at 199 C at TD. There were 3 stimulations conducted. One was in the open hole section. It's 47 meters in length. And then 2 stimulations in the cased section. The reason to do it in the case section is in the past, EGS systems stimulation projects have relied on long open hole sections. These sections are typically, hundreds to, they even could be 1,000 meters long. When we try to stimulate open holes, if there's no packers involved, the fluid will go out the first zone, the lowest pressure zone. And it's very, very difficult to get fractures to open below that zone. My team and I are very concerned about running open hole packers. They have a high failure rate. We think that the failure rate can be reduced by stimulating regions in the case portion of the hole. So we run packers and bridge plugs in the case portion, just like in the oil and gas industry, perforate the casing, and then stimulate the fractures behind the casing. This was done in the first well that we tested, and we were able to stimulate fractures that were optimally oriented at relatively low pressure. So we demonstrated it could be done. And we determined where those fractures are using the FMI, Formation Micro Imager logs, which allow us to evaluate the orientation of the fractures, and in our case, fractures that are northeast trending will be the ones that will open up most easily. So the reason simply is we think we will have much better control on the locations of the fracture zones that are stimulated by using packers and bridge plugs inside a cased well.
Okay, thank you. And I also have another question. Can you comment on the quality of the wallbore walls, such as smoothness when drilling with the PDC bit?
They're very smooth. They're very round. We haven't seen breakouts. So we've run gyros, so we have controlled the orientation of the wells very well. Using mud motor, we're using top drive for the rig. Yes, they look like gun barrels. They are very, very smooth.
Okay, thank you.
Can I ask a question about the casing test? Do you lose efficiency of, say, the energy transmission through the perforated casings because of a hydraulic resistance?
We certainly will.
But it still overwhelms the disadvantages in open hole packers.
I think so. Even the project in Finland not too long ago in open hole, they used open hole packers. It was 100C. One of the packers failed. We think by using Viton the right rubbers, and some of the projects are to develop higher temperature packers, that ultimately will be a better approach than trying open hole. A good example was a project I did at Raft River, and I don't want to digress too much, but we drilled a well. We drilled it to, I'm sorry, I'm going to use English. No, 5,500 feet. There was a fracture at 6,400 feet. It was maybe 7,000 feet total depth. The only fracture that ever took water was the fracture that was originally present when we drilled the well. It was a small cool zone. And we injected cool water. It's a low temperature system. It's like 180 C. It's a relatively low system. Injections around 100, 110 C. We went from half a barrel a minute or 20 gallons a minute, half a barrel, to 1,700 gallons a minute in the same fracture over time just by injecting cold water. So what is that? 400 barrels a minute. And we were never able to open up another fracture in that well, despite several stimulations. So that's the reason we're going to the oil and gas type approach of multiple stages, couple of 100 feet long, with packers and bridge plugs. I'm not sure how we'll do it yet. We're still looking, sliding sleeves. We're using ball, perf, and simple perforation programs. But right now, the packers have failed, and the bridge plugs have failed. They failed to set. They failed to stay set. And so we're looking at higher temperature.
Okay, thanks for the answer, Vasiliki. Further questions?
Yes, I have a question to Albert from Ignacy regarding the approach that how do you approach or you manage to approach local stakeholders regarding the issue of induced seismicity when a new project is planned? What steps do you take and what steps do you recommend that should be followed by the investors?
So thank you. So I gave just a short answer to Ignacy, but it's a quite interesting question and quite complex. It's clear that, for instance, in the French law, we are not obliged to involve local people. We involve local people at the end of the process, meaning that people, they heard that you will do a project and then they are afraid. So it's clear that if you want to do project, you need to involve stakeholders, various stakeholders. Local people means association, but also local politician, and you need to present them your project at the early stage of your project, not when the project is already finished. Otherwise, you will have a big issue with them, because of now everybody heard, at least in our area, induced seismicity issues, and most of the people in Strasbourg now they felt induced seismicity, and some of them they have damage on their houses. So we think that now we need probably years to convince people to go to deep geothermal energy, at least in Strasbourg. In the area of Sousse and Rittershofen, which are located roughly 50 kilometers north of Strasbourg, we have a good connection with local politicians because we operate the plant for many years and nothing happened. So at least we can prove that we can develop this technology by minimizing and avoiding any concern. And the best things is to make visit to show them that it works with no concern. So to convince people is to show example, concrete, tangible example. But I haven't, I would say, a clear process to propose, but at least it's to be at the early stage closest to the people and show them, organize visit, show them how it works, and explain. So that means you need to communicate a lot.
Okay, thank you. And I have one from Emilio to Antonin, if I may. How did you identify the site and how did you decide the exact location of the wells?
Well, thanks for the question. I've tried to address this question and answer to Emilio. So you can read it, but briefly, it was actually a coincidence when there was an kind of enlightened, let's say, or enthusiastic city leaders in Litoměřice approached by some experts dealing with geothermal energy and having experience with projects in Susufore and other locations, and they persuaded the mayor that it would be great to do some detailed geophysical research, which happened in 2004 and 5, and this research proved that the location is actually very good in terms of expected fractions or fracking zones. Sorry, I'm not a geologist, so I'm not really precise. And based on this research, they applied for subsidy from the Ministry of Industry for drilling the first geothermal well, and they got this subsidy. And then in 2006 and 7, the geothermal well was realized. And since that time, actually, it proved to be it proved that the expectations were quite okay in terms of thermal gradient and geological profile, etc. And therefore, city decided to go on and support this major project, and which I presented in my presentation. So that was actually the story of the beginning. So not big science behind that in the very beginning of the project.
So Antonin, was it always planned as an EGS project or as a hydrothermal project in the beginning?
Well, no. It was EGS or HDR project since the very beginning, because there are no really good conditions for the hydrothermal systems, or these localities are already occupied by spas or somehow protected for other purposes. So yes, it was the hot dry rock or EGS system since the very beginning.
Maybe I can add something, Gregor, because Emilio asked me the same question.
Yeah.
So I said some words on the chat, but I could make more briefly. So in fact, in this area, when we start to do the project, nobody did any exploration, because the concept for purely hot dry rocks. So that means we have to deep drill in hard rocks. So we don't care about geology. So I am a bit short, but somewhere nobody looks about, I would say, data. But because we have to make a well, when you make a well and to cross the sediment, we use 2D vintage seismic data and also shallow oil well, just because we have to penetrate the sediment. But otherwise, for the target, nobody did any exploration. And by drilling, we discovered that we have some channels, power channel in the basement, in the fractures. So we start to say how to image the basement, which is for me a key point. The answer we find is 2 years ago, we did a 3D seismic survey, roughly 200 square kilometers in this area, and we were able to image the fault to the top basement. And then now we can extrapolate a bit the fault system inside the basement in order to have better, I would say, structural map. But we are just imagining the top basement, not inside the basement. So it's a beginning of the answer. But at least we know the geometry of the fault system better than in the past, because in the past we have all 2D shallow, and now we are 3D, and we reach the top basement. So for us, it's very, very important.
Yeah, and sure, gravimetrics and magnetics together with the 3D seismic could be a great combination for getting insights of the basement structure.
So maybe we did gravimetry, we did MT, and last October we did, I would say, a resistivity survey with my French colleague of the French Geological Survey BRGM and University of Strasbourg. We did a survey we inject some power in the ground, and then we map. We have a series of roughly 100 sensors, and we try to map resistivity on the same area where we did the 3D seismic survey. So now we have to combine that. So it's not done yet. It could be maybe for another seminar. People are working on that data set, but we are going in that direction to, as you propose in your presentation, to combine various methods. Even they are not the same resolution, you learn things, and you have a physical message, which is quite important. So sometimes it's seismic, sometimes it's density, sometimes it's magnetic, sometimes it's resistive. If you can mix them clever and make some forward modeling and maybe other things, you can learn a lot.
Yeah, and if I understood well, the second plant you show the data, though, so it's Rita Schaffen or something like this.
Yes.
It was very important to know the geology because it saved lots of money in drilling.
Yes, but at that time we use also. We did just before drilling the second well, we drilled the first well, and before the first well and the second well, we did a 2D seismic survey in order to try to find the best trajectory for the second well.
So sorry to interrupt the discussion, Emilio and Albert, because we're coming to the end of our slot of our workshop today, and I would like to bring it back to the topic of Geothermal-DHC, of the cost action. I would like to ask the presenters one quick question from a strategic point of view. So where would you see EGS in 10 years from now? And would you think that the application may move forward just from electricity focus, also on the heating focus, or you don't see any option? Maybe first, I would like to ask this question to you, Albert. What are your vision for the next 10 years on EGS?
So my wish is to do many projects, as you imagine, but if I think in terms of application, it's clear that electricity, for instance, in France, we have no more feed-in tariff. So it's clear that we will not do probably electricity in the future because there is no more, but there is no more also economy. Because with a heat project, you need to find a huge factory, as we did in Petrothermal. They use the heat 24 hours a day, all the years. So in fact, we need to be clever, to be smart, to combine good applications. And when application means it could be heat, it could be greenhouse, it could be extracting the lithium. It could be also partly electricity with ORC, for instance. But a single project with only electricity I think it's not our future. We need to be clever and combine with several applications. So I think it's a message I can give.
And maybe to Joe, what is your vision, let's say 10 years from now, for EGS in the United States?
I'm very optimistic. I think this is an absolutely huge program that the DOE has put out. There's a lot of effort going in. At this point, we are not expecting to generate electricity, but I see the work we're doing has broader application. Obviously, generating electricity is my personal goal, but we're limited by transmission lines. You know, there are lots of hot rock. That's not a problem, and there's a lot of hot rock in the West. But finding transmission lines can be a problem. I see ultimately the greatest application for this in direct use. There are many places where permeability is just not available. And if we can learn how to generate this permeability, then that will be a major stepping stone. And it will also be very, very significant for natural geothermal systems or conventional geothermal systems. Because at least in the US, the margin of conventional geothermal systems is the place where there's no permeability. With plenty of heat, that's not an issue. And these systems can be expanded considerably, but producing the permeability is critical. So I see the techniques that we're developing being applied both to direct use around the world and to conventional systems as well.
Thanks a lot for your statement. Antonin, maybe your final statement.
You mean what I think about the future?
Yeah, your personal or expectation or your vision on EGS, maybe looking at Czech Republic.
Well,
yeah.
We are reaching a great milestone. If we get funding and we will keep in touch with these great projects and successful projects and the community that have given us or provided us with a great support for last decades, let's say. And it's still inspiration for us. Then if we manage that, this will be success, I would say, not only for the Czech Republic, but also for Europe and the EGS or geothermal sector as a whole. And if we failed in terms of not getting the funding, and that means not realizing the project, I'm afraid that it will take another 5, maybe 10 years. Then there will be a new window of opportunity to really start such a huge project. And it's still a question if the city will support this project, and if the Czech Republic as a state will support geothermal energy, because the biggest obstacle is still that there is no functioning project that will prove that the EGS systems work and are safe and reliable sources of energy. So this is how I see it. But I would like to join or follow Albert and Joseph's optimistic view, and I hope we will succeed. And I believe this will be a great time for EGS sources and projects.
Thanks a lot, Antonin. One final statement, Emilio.
Yeah,
you're not a geothermal expert, but maybe from your point of view or for Spain.
Yeah, I told you. So I'm not a geothermal expert, but I may say I am a structural geologist pretending to be an exploration geologist and geophysics. So just kidding apart. So I really would like to see hydro, especially deep hydro geothermal energy, working in 10 years in many production plants. Really would like to see. But actually, for doing this, we really need to screen well the subsurface from a geothermal point of view. And in many regions, we haven't done this so far. So I think much work is left to do to really identifying lots of potential structures in the subsurface.
Okay, thanks a lot for your statement, Emilio. So we are coming now to the end of our workshop. Thanks all for joining. You will receive a documentation of it. Just one hint, our next webinar will be on the 16th of April. We'll address life cycle analysis in geothermal heating and cooling networks with presentations from colleagues from Greece, from Spiros and Maria. Please sign up to our newsletter or join our network. It's open, it's voluntary, so there are no obligation. And in contrast, or in turn, low funding. Maybe we see each other again and keep contact also on petrothermal energy use. So there is a dedicated working group on petrothermal inside our cost action. And thanks a lot for joining, and I wish you a pleasant afternoon or evening. Yeah. Goodbye.
Bye-bye, Gregor.
Bye. Thanks all for joining and giving your presentation. Thanks a lot.
Thank you, Gregor. Bye.
Bye.